Welcome to Math 361, Statistical Methods 1. This is the Week 4 online lecture video covering random variables. In this lecture video, we'll introduce random variable theory. Recall from the Introduction to Probability lecture videos, we were interested in modeling a real-world random experiment. And the start of our mathematical modeling of that random experiment was to build a sample space. And within that sample space, there were sample points. So in this example, the real-world random experiment is rolling 2 dice. And so in this case, an outcome of getting a 3 and a 4 on the dice would map to, say, an ordered pair, 3, 4 in my sample space. But quite often, I'm not interested in necessarily the particular outcome of a random experiment, but with some measurement taken on that outcome. This is important for us in terms of our mathematical modeling because if you think back to the first lecture in the course, when we talk about the science of statistics, I'm going to be taking subjects from my population, either via census or via random sampling, and taking measurements on them, their age, their income, number of children they have. So I don't necessarily care about the particular person I choose in my sample. I care about what some measurement I'm taking on that person. So random variables are what we need in our math model to start taking measurements on sample points. So given one random experiment in the real world and a corresponding sample space in math world with some sample points, I could define many different random variables. I could consider the outcome 3, 4, that sample point, and be interested in the sum of the values. I would map or associate that sample point 3, 4 with the number 7. Or if I'm interested in the product of the values, I could map 3, 4 to the number 12. Or any other possible calculation I want there, I could define a random variable that does that. So the idea here is I have essentially an input that is a sample point and an output which is a real number. So going back to college algebra, this really is the notion of a function. So if I visualize my function with a function machine, that's what's in black in the middle there, labeled uppercase x, the inputs are going to be sample points, lowercase s. They come from a domain. That's the set of all inputs to this function. That is our sample space. So a sample point falls into the machine, the gears churn, it does something to that sample point, and what we get out of it is a real number. Now, in algebra, we'd call that f of x or something like that, but here the input is s, my function name is uppercase x, so I use this weird notation, uppercase x of s. That's how that's read. Don't worry, we won't use this notation pretty much beyond this video, but to really emphasize the fact that these random variables are neither random nor a variable. It's really a function defined on the sample space that outputs real numbers. So why do we call them random variables? Well, in one way you can think about it is that before you perform the random experiment, you don't know what value this random variable will take on. Once you roll the dice and you get a 3 and a 4, then you know this random variable will take on the value of 7. So in that case, the value that the random variable takes on is random before you actually perform the random experiment. And why do we refer to it as a variable? Well, we'll see that it is advantageous to us to start manipulating these random variables as if they were standard variables from college algebra course. Adding them together, multiplying them, or things like that. So kind of to summarize what we've talked about so far, some vocabulary here. A function whose domain is a sample space and whose range is some subset of the real numbers is called a real-valued random variable. A random variable is called a discrete random variable if it can assume at most a countable number of values. So for our example with rolling 2 dice, there are 36 possible outcomes of that sample space, in that sample space. However, the random variable, if we're looking at calculating the sum of the two numbers, can only take on the values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So that is a discrete random variable. It is finite, right? I can list them all out and it ends. What do we mean by countable? We could have infinitely many possible values. Imagine a scenario where I was flipping a coin and I wanted to count how many flips it would take until I get heads. It could take one coin flip, it could take 10, it could take 1,000,000 or 10 trillion. In this case, there are infinitely many possible values that random variable could take on, but I can still count them. Finally, what we're really interested at the end then, of course, is once I defined a random variable, I'm going to be interested in how likely is it that the random variable takes on a particular value. So what's the probability that I get a 7? So here we define a function, we'll call it p, and the notation here is kind of strange. Essentially, this is a function that will take an event and assign to it a probability. So we call this a probability distribution function, or because this is a discrete random variable, we call it a probability mass function, or a PMF. So the notation is p of x. So if I had this setup here with this rolling 2 dice, and I wanted to know what's the probability that I get a 7 on the roll, I would find p of 7. But what does that mean, p of 7? Because I can't find probabilities of numbers, I find probabilities of events, which are subsets of the sample space. So several different notations instead of p of x or p of 7 in particular. The second one there is p, and it says of uppercase x equals lowercase x. So I want to find the probability that I get a 7 here. I would write the probability that uppercase x equals 7. And what I need to know is that both of these alternatives really are shorthand for that third notation there. And this uses something from set theory called set builder notation. And if I were to just read this out to you left to right, this is the probability, and now there's a set. It's for S is an element of uppercase S. So another way of saying that is the set of all sample points in the sample space. And that vertical line here is not given if it were, like in conditional probability. We read that as such that. So this is the set of all sample points in the sample space such that x of s is equal to lowercase s. So the event I'm finding the probability of is the set of all sample points that the random variable associates with the number 7, let's say, in particular there. We'll never use that final notation when actually solving problems. We'll use the shorthand notation to begin with. But in the back of our minds, we have to remember I can only assign probabilities to events which are sets that are subsets of the larger sample space. So for the next few slides, I want to go over some basics of random variables, how we use them, and some calculations we can do with them. And we're going to go through them using this example here. Suppose you roll a die. We're playing a game. If it comes up a 6, you win $100. If not, you do get to roll again. If you get a 6 on the second roll, you get $50. Now, if you don't get a 6 on either roll, you lose. You get nothing. So here we're going to let x be a random variable corresponding to the amount you win at this game. Find the range of the random variable and its probability distribution function. Summarize the results in both tabular and graphical form. So here, once again, I have to look at what does the sample space look like. If I were to really think about the sample space, it would consist of sample points like 2, 5. That would be rolling a 2, then rolling again and getting a 5, and I'd want my random variable x to map that to 0 because I never got a 6. I could also have a sample point that's a 1, 6, meaning I got a 1 in the first roll, a 6 in the second roll. That would get mapped to a value of 50, right? Because I would win $50 in that case. There's also a sample point that corresponds to a single roll and getting a 6. That sample point corresponds to $100. Now, once again, I don't care about the particular things. If I get a 2 and then a 5 or a 3 and then a 2, in the end, I still win $0. So the idea here is I'm going to define a random variable that will measure my winnings by mapping sample points to different dollar amounts. Now, the range of my random variable would be all the possible values the random variable can take on. So from my problem description, there's only 3 values. So this would be a finite, discrete random variable. It can take on a value of 0, 50, or 100. So one way of working through this problem would be to use a tree diagram. That's what I have in the upper left side there of the work. I can think about roll 1, I either get a 6 or not a 6. I could have 5 different branches there, or 6 different branches for all 6 possible outcomes, but all I really care about is getting a 6 or not a 6. And then roll 2, a 6 or not a 6. And now each path through that tree diagram from the very start to the end of a path is going to give me a different result. In this case, the upper path, just getting a 6 gets me $100. Getting not a 6 and then a 6 is $50. Not a 6 and not a 6 is $0. All right, so those are my 3 outcomes. So on the far right of this slide, I have my table where the first column is lowercase x. Those are the values that my random variable can take on, 0, 50, and 100. Now, how do I find p of x, the second column there? Those will be that's the probability mass function. Well, looking back at my tree diagram, what I did was I labeled each branch with the likelihood there. So on roll 1, the probability of getting a 6 is 1 out of 6, and the probability of not getting a 6 is 5 out of 6. Now in roll 2, that 1/6 is really a conditional probability. It's the probability of getting a 6 on roll 2 given you did not get a 6 on roll 1. Likewise, the not 6 on roll 2 is really a conditional probability of not getting a 6 on roll 2 given you did not get a 6 on roll 1. So when I'm multiplying through now from start to finish, just like we did conditional probability, what I'm really using here is the general multiplication rule again. Now these probabilities are easy to come up with for filling in the chart there in purple because of the independence of one roll and another. Right? So it doesn't matter that I did not get a 6 on roll 1 and roll 2, the probabilities will be the same. So by multiplying through each of them, that's how I get the probabilities in green in the last column on the right hand side there. For 0, I had to multiply 5 6 times 5 6 to get 25/36. For $50, I multiplied 5 6 times 1 6 to get 5/36. And then for $100, I simply had that first path through the tree diagram, which is just a probability of 1/6. Now to sanity check yourself here, just like when doing conditional probability tree diagrams, after I've got all my probabilities there, I want them to add to 1. If they don't add to 1, either I've forgotten some values in the range of my random variable, meaning there's a row missing from my table, or I've incorrectly calculated those probabilities. Note here that this random variable, there's 3 outcomes, 0, 50, or 100 of this random variable, but every sample point corresponds to one of these values. Right? So I got to make sure I come up with all of them. Quite often when working these types of problems, I find the students will forget usually like a $0 option or something like that, where you win nothing. You can't exclude that though, right? If I just had a table with $50 and $100, my probabilities wouldn't add up to 1 here. So I want to make sure I include every possible value in the range of that random variable. So assuming I get my sanity check here, my table is done. This is the tabular form now. Think about every time you define a random variable, automatically think about the range and then think about the probability distribution function or the probability mass function. They always kind of go together with one another. Squeezed into the bottom here is a graphical version where along my horizontal axis I have the x values, and then on the vertical axis I have my probabilities. Now, even though the random variable only takes on 3 values, my probability function is defined for all real numbers. So that's why you see just these spikes at 0, 50, and 100, and essentially a value of 0 everywhere else. Moving on, the next question is, find the expected amount you will win. Well, expected is in quotes there, so what are we talking about? I either win $0, $50, or $100. How do I know what I expect? I expect 0 maybe because that's the most likely. Well, when we talk about random variables and we mention what you expect to get, the notion of expectation, this is actually a special mathematical definition. It's essentially the random variable equivalent to the mean of a data set. So let's define mathematical expectation. Let x be a discrete random variable. The expected value or mean of the random variable x, usually denoted by e of x, although sometimes we'll use mu or mu sub x if there's multiple random variables in a problem, is given by the following formula. Now, once again, on the right-hand side, that's a summation where I've now used the subscript k there. It goes from 1 to n, so those are saying that there's n different values that the random variable can take on. And the way I calculate this expected value is I take each value that the random variable can take on and multiply it by the likelihood the random variable takes on that value. I do that for each value, and then in the end, I sum up all those products. Now, before we go and perform that calculation for the example, let's go turn to Excel to get a better understanding of what expectation is really telling us. So moving to Excel here, I've got a simulation set up where I am rolling a dice twice, or rolling 2 dice if you want to think about it like that. I have Excel calculate a random number between 0 and 1, multiply it by 6, so it's between 0 and 6, add 1 to it, so now it's between 1 and almost 7, and then I round down, so I get something between 1 and 6 in the end, 1, 2, 3, 4, 5, or 6. So here, value of roll 1 is 4, value of roll 2, same formula, is 2. I sum those two results, 6, and now what I do is I find the average sum of 2 rolls so far. So out of 1 roll, that's 6. On roll 2, I get a 4 and a 5, that's a 9. So 9 plus 6 is 15, so I've averaged 7.5 so far. So I do that every time I re-roll the 2 dice. I get a new sum, and now I re-average all my sums so far. So this last column is a running mean of sums. Now, of course, what I want to do is I want to go and visualize it. So on the horizontal axis, you see number of rolls. There appear to be about almost 2,000 rolls. Pretty good. On the vertical, I have the average sum of rolls. You see that it bounces around a bit early on, but now it's going to start approaching a value of 7, it appears. If I go and re-simulate everything, the graph changes a little bit, but my average sum of rolls approaches 7. Do it again. Still approaching 7. Start a little low this time, but still approaches 7. So I see that law of large numbers coming into play here again. So that expected value, right? How do I interpret that calculation? Well, if I were to come up with a random variable and actually come up with the entire probability function for a random variable that assigns the sum of 2 dice rolls, I would see that if I went and calculated the expected value using the provided formula, I would get 7 out of it. Right? So I think of expectation or expected value as a long run, how many runs, who knows, right? But a long run theoretical average result. Right? It's the average or mean value a random variable takes on in the long run. Returning to our example now, we'll calculate the expected amount we will win. So to calculate e of x, I take each value in the range of the random variable. In that case, it's 0, 50, and 100. I multiply it by the corresponding likelihood that the random variable takes on that value. So I have 0 times 2536 plus 50 times 536 plus 100 times 1/6. After I take that sum, I get approximately $23.61. Now note, I should not be concerned that the expected value of the random variable is not one of the actual values the random variable can take on. $23.61 is not in the range of x here. But as we saw from the Excel demonstration, I interpret this number as if I played this game over and over and over again. In the long run, however many games that would take, if I averaged or took the mean of all my different winnings, it should approach $23.61. So on average, I'd be winning $23.61 every time I played the game. A lot of times I'd be winning 0, sometimes I'd get 50, and occasionally I'd win $100. Now, one of the good uses for this expectation would be to look at whether it'd be worthwhile for you to play a game. Imagine a casino charged $25 to play this game. Now, most of the time you'd win nothing, but you have 2 chances of winning some money. Right? You roll a 6 right away, you get $100. That's quadruple what you were going to pay. If you get a 1 through a 5 and then get a 6 on that second roll, you get a second chance to win. However, regardless of what happens in a couple wins, the idea is if you played this game long enough and you were paying $25 per play, in the end, you'd be losing money on average every time you play the game. Obviously, this is tantamount to the house always wins. This is the idea behind casino games, is that they can come up with an expected value that they will pay out, and then they will then charge slightly more than that because they have thousands of people coming, playing thousands of games, and they actually will realize that long-term return. Along with the notion of mean for a random variable, which we now refer to as expected value, we could also talk about the variance and standard deviation of a random variable. So this would talk about the variability of the values the random variable will take on. So here, let x be a discrete random variable. The variance of x, denoted sigma squared again, or sometimes with a subscript x on there. Sometimes you'll see me in upcoming slides use VAR of x, is given by the following formula. Note here it is an expectation. So I'm defining variance in terms of expected values. And what I'm taking the expected value of is this new quantity. It's a random variable x minus a constant mu. So that seems a little odd there. So that's kind of like a deviation, and I'm going to square it. That should seem similar to when we were calculating variance of data sets. It was a sum of squared deviations over n minus 1. So here, this looks a little odd if you think about what these letters and Greek letters and regular letters actually mean. It's a random variable, which is a function, a machine, minus a number. That doesn't really make sense. But this is where treating a random variable as a variable becomes very handy. What that is inside the parentheses for expectation is actually a new random variable. I'm taking x, you imagine taking all the values in the range of x, subtracting mu, that, $26 or so, from each of those values, and then squaring it. And those would be, that would be the range of this new random variable. Now, fortunately, there's a nice mathematical theorem that says, okay, this is a new random variable created for my old one. If I'm going to do any sort of expectation calculation, I need to know the probability mass function of this new crazy random variable. But it turns out we actually don't. If you see on the right-hand side of the slide here, how do we actually calculate this expected value? All I do is simply take each value, subtract the mean from it, square it, so that's a square deviation, And now I multiply it by the original probability mass function. That p function is for random variable x, not random variable x minus mu quantity squared. Right, so that makes this very easy to calculate. Start with x, then find x minus mu for all the different values, then square those results, and now multiply by the probabilities and sum in the end. Now the standard deviation, denoted by sigma, is once again just the square root of variance. Now I mentioned when we talked about calculating variance for a data set that your textbook had some shortcuts for calculating variance by hand, but you should never memorize them. The formulas are horrible. Well, now we've reached the point where when we calculate variance for a random variable, it turns out that the shortcut formula is actually fairly easy to use. Now, where this shortcut comes from is essentially looking at that quantity x minus mu squared inside the expectation, treating that as an algebra expression. Oh, and I have a binomial expression that's squared. Why don't I essentially FOIL everything out and see what I get at the end of it? So if you do that, you get this alternative formula for calculating the variance of a discrete random variable. It's the expected value of a new, yet again, random variable x squared minus mu squared, where mu is the original expected value of x. Now, just like before in the previous slide, I don't know the probability mass function for this new random variable x squared, but I don't care. I have a nice theorem that's not mentioned here that says, okay, let me go back and instead of doing x times the probability of that value of x, I do x squared times the probability. And everything works out correctly there. So let's go back to our example and actually put these formulas to use. And I'm going to calculate the variance both ways. So using the straightforward definition, the variance of x, where I'm now using the VAR notation to denote variance, I start with taking 0, subtract from that the 2361 mean, square that result, and then I'm going to multiply that by the likelihood that the random variable takes on the value 0, which is 2536. The next term has a 50 minus 2361 quantity squared times 536. And finally, the last quantity will have 100 minus 2361 quantity squared times 1/6. Right? So it's always a deviation away from the mean for each value that x can take on, but I'm squaring it, and then I'm multiplying by the likelihood that the random variable takes on that value. And in the end here, I get $1,456.40 square dollars. So just like before when we were talking about a data set, variance is in these non-standard units. That's why we would talk about standard deviation as well and take a square root, so we're back into dollars as our units. Now going and calculating this the other approach, using the other formula, the expected value of x squared minus mu squared. Now I'm going to start with 0 squared times 2536 plus 50 squared. So I'm not calculating any deviations here. 50 squared times 536 plus 100 squared times 1/6. So that's the first expected value of x squared, is those first three terms that are being summed up. And now at the very end, I'm subtracting off 2361 squared. Now in the end, I get $1,456.46 squared, which is slightly different from the previous slide where I had 456 and 40 cents. Here I have 46 cents. Well, that's because at the very end of the previous line, I squared that mean, but I didn't use the actual mean. I ended up using the rounded to 2 decimal places version of the mean. So rounding, I mentioned this earlier, rounding mid-calculation ends up causing you some issues later on. Either way, I get what is essentially the same quantity. One final thing I want to look at now. We've been able to come up and define the probability mass function for this random variable by determining its range and then doing some probability calculations to come up with the probability mass function. Once I have the range and the probability mass function, or the distribution function, I can then calculate quantities like expectation and variance and have some understanding of what they are or how to interpret those numbers. My final example here is repetition of a random experiment. This will be important for us later on because when I select a person at random from a population for my sample and take a measurement on them, I'm going to repeat this process. Right? I'm going to take multiple random samples. Sorry, I should say I'm going to take one random sample, but that requires me to repeatedly pick a person out and take a measurement. So I played this game 3 separate times. How much should I expect to win on 3 plays of the game? What will the variance of the amount I win be? So the idea here is that I want to play the game 3 times and add up the results. So what I need to do here is define a new random variable, we'll call it y, and what I will do is make that the sum of x sub 1 plus x sub 2 plus x sub 3, where the subscripts denote the gains, and each of these random variables is independent. What happens in game 2 is not affected by what happens in game 1, and identically distributed. Meaning each of these random variables has the probability mass function that we originally defined. Now, why do I need 3 separate versions of x here? Well, if I didn't have those subscripts and I just had x plus x plus x, treating those as variables, that's repeated multiplication, I could replace that by 3x. But that says then, you can imagine on the first run of this game, if I won $50, random variable y would then take on the value 3 times $50, which would be $150. But that then requires me to win the same amount on every play of the game. But I don't want that. I want to have the flexibility to maybe win $0 in game 1, and then $100 in game 2, and then $50 in game 3. So I'm using the same variable here, uppercase x, because they all come from that same probability distribution, but I am using different subscripts so that I can distinguish one run of the random experiment from another. Now, ultimately, what I want to do here is I want to find E of y, the expected value of y, and the variance of y without knowing the probability distribution for y. That is my goal, because that sometimes is very hard to come up with. So it turns out there are some nice rules for manipulating expectations and variances. So if we let x and y be any random variables and let c be a constant real number, the first rule is the expected value of a constant is simply that constant. Rule 2 is the expected value of a constant times a random variable is equal to the constant times the expected value of the random variable. And rule 3 is if we have an expected value of a sum of random variables, that's equal to the sum of the expected values. That's important for our purposes because our new random variable y is a sum of 3 other random variables. So rule 3 will be very handy for us here. There are likewise 3 rules for variance. They look fairly similar. This time, though, a variance of a constant number is going to be equal to 0, because remember, variance is a measure of variability, and a constant doesn't vary at all, so it's assigned a value of 0. Variability of a constant times a random variable x is equal to the constant squared times the variability of x. Now, why is it squared and not just by itself, like with expectation? Well, that's because of the definition of variance for a random variable involves an x minus mu quantity squared. So that squaring in there results in the c squared on the outside here. Finally, if x and y are independent random variables, so there's a new kind of additional requirement there, then the variance of x, now I had to draw in because there was a typo, plus or minus y. Doesn't matter if I'm adding or subtracting the random variables, I end up adding the variances. All right, that's a key thing there. So if I had the variance of x minus y, and they were independent random variables, that would be equal to the variance of x plus the variance of y still. Note, this slide is also another argument for why we talk about variance and standard deviation. They're so closely related. Why do we have to have different names for both of them? It's because sometimes formulas depend on standard deviation, and other times, like this slide, I have some theorems here that deal with manipulating variances. These properties wouldn't hold if I was trying to manipulate standard deviations. Right, so that's a key thing. If I'm given standard deviations in a problem, I would actually have to move by squaring to the variances before manipulating these guys around. Now, once again, these rules for expectation and variance, we won't be calculating them for homework or that type of stuff. They're really going to help us when we get to kind of the theoretical derivations of some other random variables in lecture this week. So going back to this, if I played a game 3 separate times, how much should I expect to win? What will the variance of the amount I win be? Well, my work would look like this. I would define y to be the sum of x1 plus x2 plus x3. The expected value of y is the expected value of that sum, which using the third rule of expectations is simply the sum of the expected values. Now, each one of those is identically distributed, meaning they follow the same probability distribution function, and they have the same range, so therefore they all have the same expected values. So I get 2361 added together 3 times, resulting in an overall expected winnings of $70.83. For variances, this works the same. The variance of the sum is equal to the sum of the variance because I'm assuming each run of the game is independent of the other runs. So independence, the necessary independence criterion is met. And I just add up those variances 3 times. I get $4,369.20 squared. So in lecture this week, we will start off by looking at a similar example to this one, where we start off with some description of a random experiment. We'll define some random variables on the sample space for that random experiment, do some calculations, and make sure we're kind of all okay with the basics of these calculations. Now, where we're ultimately going with random variables this week is we'll be looking at some common situations, some common random experiments that we come across very often. And what's happened is that over the years, mathematicians and statisticians have looked at these scenarios, studied the random variables that result from them, the probability mass functions, and done all the work for us. So what will be important for us is to be able to look at a description of a random experiment and say, hey, you know, that description sounds like this type of random experiment, which results in this type of random variable. For example, earlier I mentioned how many coin flips it would take before I get a heads. Well, what I'm really interested in doing there is performing a repeated random experiment of flipping a coin and counting how many trials it takes before I get a success, getting heads. That's an example of the second common discrete random variable mentioned here, a geometric random variable. So if I see that scenario, I'm counting up how many runs until something happens, I know that's a geometric random variable I'm interested in, and therefore there are formulas and theorems all about it I can go look up and use. Now in our course, we'll be focusing on the first one here, a Bernoulli random variable. We won't do much with it, but it will lay the groundwork for then talking about the second one in red here, a binomial random variable. We'll skip geometric, that's not in our textbook. Hypergeometric we've actually already talked about without using random variables. Hypergeometric is similar to the problems with having a bunch of socks of different colors and you're randomly selecting them and trying to figure out how many you get of a certain color. That's kind of the hypergeometric scenario. There's a lot of combinations being used in that calculation. A negative binomial we'll talk about not in detail, but I'll mention in class this week once we know what a binomial random variable is. And finally, a Poisson random variable, the last one, is actually in our textbook. It's the last section of chapter 5, but we will not be talking about it due to our several days of missed class. So in summary, random variables, you should think about already having a mathematical model of your random experiment. You have a sample space and some sample points, and random variables come into play when we want to take measurements on those sample points. We don't care about the particular outcome or the particular sample point. We care about something measured on that sample point. Discrete random variables are when the random variable can assume at most a countable number of values that could be infinite, but usually it's a finite number for the examples we deal with. Once we have a discrete random variable and know its range, we always talk about a probability distribution or a probability mass function, where this allows us to assign probabilities to the different outcomes of the random experiment. For rolling 2 dice, I want to know how likely it is that it gets that it takes on a value of 7, that I get a sum of 7 those 2 rolls. Well, the random variable will map things like 3, 4 or 1, 6 or 2, 5 all to the number 7. And then if I collect all those sample points that map to 7 into a set, that gets me the event that I want to find the probability of. That's what my probability mass function is doing for me. Once I have all that, I can visualize it in a table or a graph. I can then talk about long-run behavior, find the expected value of a discrete random variable, and I have to remember how to interpret that now. It's the long-run theoretical mean value the random variable takes on. If I perform the experiment over and over and over independently, took all the results and averaged them in the end, it should approach the expected value of that random variable. And finally, although we won't be doing too much of this on our own, just in lecture through derivations for other work, there are rules for manipulating expected values and variances that are very handy. See you in class on Saturday.